Hello and welcome. Today we are going to be talking about performance. That is how fast your R code runs and how much memory it uses. So we're going to be trying to write R code that runs as quickly as possible. And I think the main lesson here is that if you want your code to be performant, that is to run fast and use little memory, you really need to measure it. And nowadays there are really good tools in R for measuring the performance of your code. Back when I was in graduate school, I was a MATLAB programmer. And as I was learning to program, someone told me I was struggling with a slow piece of code, and someone told me, well, you've got to profile your code. And I didn't know what that meant. So he showed me the MATLAB profiler, which is a really nice tool. It basically looks at every line of your code and sees how long each line is taking. And that kind of blew my mind and has kind of changed how I think about developing code. You really have to measure it. Back in those days, there weren't similar tools in R to profile your code, that is to measure it. Nowadays there are better tools. The one we're going to be looking at today is called profvis, and I think it's pretty good. So we'll show you how that works. So what we're going to start with, though, is just some general advice on writing good R code that performs well. There's not going to be a lot of general advice. My real general advice is that you have to measure it and you have to test it. But we will look at a few things. So let's open up in our script. Our script is open. And so we have a console on the right here. And the script is called performance.r. So let's start with some general advice. The main thing you'll hear is that quote-unquote vectorized operations are faster than non-vectorized operations. What people mean by that is they say is that if you can call a function that operates on a vector that operates on the whole vector, then those functions are generally faster than writing a loop over the elements of a vector and modifying each one in the loop. So let's just look at an example. So I'm going to create a vector x. It has 10 million entries. There are 10 million normals. And I want to simulate from the log normal distribution, which just takes normals and exponentiates them. So I'm going to look at two ways of doing that. For the first way, I'm going to initialize a vector of NAs called y. That's the same length of x. And then I'm going to loop over j in 1 to the length of x, and then assign to the jth element of y e to the jth element of x. All right, so that's the first way. The second way is we're going to use the vectorized version. That's this one, because the function exp, if you give it a vector, it will exponentiate each element of the vector. Okay, so let's run this code here. And the way I'm going to measure the code here is kind of the simple way. I'm using proc.time. So right here, I'm starting a timer. Basically, well, I'm not starting a timer. I'm measuring what the time was here. I'm running this piece of code. I'm measuring it again after it's done. Running the other piece of code here and then measure it again. And then going to print out the differences. So T2 minus T1 will be the timing for the first non-vectorized. And T3 minus T2 is the timing for the second one, the vectorized. All right, so let's just run all that. Okay, so that ran pretty quickly. You can see that the non-vectorized, the loop one, took 7/10 of a second. And the vectorized one was much faster. It took 0.142 seconds. All right, so that's your first lesson. Vectorizing is faster. Believe it or not, you can do a lot worse. One of the things, often mistakes for new programmers, and well, not just our programmers, all programmers, is that appending to objects many times can be very slow. So we're going to perform the same operation. Here, this is so slow that I'm going to use a vector that's 100 times smaller, so 100,000 entries instead of 10 million. And instead of initializing y with to have the right length and be filled with missing values, I'm going to initialize it as a vector of length 0. And then each time I'm going to concatenate y with e to the x to the j. So on the first iteration, y is going to be an empty vector, and this will be the first entry of y. Second iteration, this will be length 1, and then I'm going to append, then it'll be length 2. So it gets built up over each iteration. All right, so let's run this code. You can see it's running very slow. Still not done. Oh, it is done. I just didn't print. Let me print. Okay. It took 6.7 seconds, which is about 10 times slower than the non-vectorized version, even several times slower than the vectorized version. 10 times slower on a problem that was 100 times smaller. So that means that it's 1,000 times slower. So this is really bad. So this is generally bad practice to do this appending as you go. It's much better, even if you're not going to vectorize, it's much better to do this up here where you initialize a vector with missing values or some other number. This also applies to things like rbind and cbind. So if you're building up a matrix or a data frame by r-binding things to each other, or c-binding columns, that's generally going to be much slower than filling up a big empty matrix or data frame and then filling it in. In some cases, it's not possible to know exactly what the length or the size of the matrix is going to be that you need to fill in. But even in those cases, you should really try to at least guess an upper bound for how big it's going to be. So even if your guess is way off, it's often still a lot faster to fill up an empty one or one with NAs. The next lesson is that you really need to use the right object for the job that you're trying to do. And the general rule is you should use the data structure that is most specific to the thing that you want to how you want to store the data. So let's look at an example here comparing matrices to data frames. So I'm just going to create an 8,000 by 8,000 matrix and fill it in with normals. So that's going to be X. So I'm just simulating 8,000 times 8,000 normals, and I'm putting them in a matrix, n by n matrix, or 8,000 by 8,000 matrix. And then I'm also going to store the same numbers as a data frame. So I'll call that D. So you could say dim X, dim D, X11, D11. So these contain the same information in them. But X is a matrix and D is a data frame. Okay. So the operation that I'm going to do is I'm going to loop over 10,000 times. And each time I'm going to generate a random index entry, so I1, I2 entry of the matrix. And I'm going to modify the I1, I2 entry by taking the exponential. Okay. So we're going to apply this to the matrix. And then we're also going to perform the exact same operation, but we're going to use the data frame data structure. Okay, so let's run this. That takes 0.22 seconds. I'm looking at the elapsed time here. And then I'm going to do the same exact thing for the data frame. And that took 1.753 seconds. So this is the data frame solution is slower because the data frame is just not, it's not the right object to use for array of numbers. So you should really use a matrix if you're working with an array of numbers. A data frame is the more general object because a data frame allows each column to have a different storage type. Could be factors or strings or whatnot. So use the right object for the job. The matrix is the kind of the simplest object that allows you to store an array of numbers, whereas a data frame is a more complicated object. And there's performance drawbacks to using the more complicated object. All right. One thing you'll often hear about performance is to use the apply functions. And sometimes they do allow you to write faster code. But oftentimes there's a more specific function for what you want to do. So this is a kind of a similar lesson to use the right object for the job. So use the most specific type of object for the job. You also want to use the most specific type of function for the job. And then, of course, time it to make sure it actually is faster. So what we're going to do here is we're going to take this matrix X, and we're going to compute the sum of the entries in each column. So the way to do that with apply is to say apply X, loop over dimension 2, and take the sum over dimension 1 as you're looping over dimension 2. The other way to do that, there's actually a built-in function called callSums, which does exactly that. It takes the sum of each column of a matrix. So let's run this. And you can see that the callSum solution was about 10 times faster than the apply solution. So I think a similar thing is going on here in that apply is a more general function. It does more things. I could replace sum with mean or minimum or whatever. Whereas callSums is designed specifically for the task of summing up the entries within a column of X. So a similar principle here to use the more specific function, just like we use the more specific object or data structure for the matrix versus the data frame. So those are a few general rules, and we will see a few more principles here as we go through the next examples. So next thing I want to show you is how to profile your code. And my method here is we're going to run through kind of a running example, and we're going to use the profiler, and we're going to identify what are called bottlenecks in the code, the slow parts. And we're going to try to fix them. And along the way, we're going to see a few more general principles as well. Okay, so I'm going to read in a data set. This is the data set from the Billboard Top or Hot 100 charts. These go back to, I think the oldest records are like 1958. I downloaded this from a website called data.world where you can get a whole bunch of other interesting data sets as well. So the task we're going to do here is we want to quickly build a data set that has the URL for the first week that each unique song appears on the list. So I printed out the first 6 rows of this big data set. By the way, dim hot has about 328,000 rows. And then there are 10 columns. There's a URL where you can look up the actual chart for that particular entry. Each entry is a song week combination. So there's a week ID. There's the position that song appeared during that week. There's the song name. There's the performer. And then there's something called song ID, which is just pasting the song name with the performer. So this gives a unique identifier for each song. And you can see that this song, Don't Just Stand There by Patty Duke, appears at least 6 times. But what we want to do here, and it also has the previous position, the peak, and the number of weeks on the chart. we want to look through the data and find the URL for the first time that this particular song appeared on the chart. Okay, so there's going to be many ways to do this. We're going to start with kind of a straightforward loop-oriented solution. It's going to be very slow. So what we're going to do is I'm going to take a subsample of the data set. This is just 10,000 of these 328,000 rows. And we're going to time the solution. Now to keep this script clean, I'm putting the functions for computing this these URLs in a different script. So it's in performancefunds.r. So let me open up that. And I've named all these different methods, just method 1, method 2, method 3, so on and so forth. So the first method, the way we're going to do it is we're going to do it a way I just told you not to, just so we can demonstrate some of these things. We're going to create empty vectors for the unique song IDs, and then an empty vector for the URL, the first URL associated with that song ID. And the way this will work is we'll loop over every row in the data frame. We're going to pull out the song ID. And then the next thing we have to do is check whether we've already looked at this song ID. So, for example, if we're looping over this data frame, the first song ID is going to be Patty Duke, Don't Just Stand There, or Don't Just Stand There, Patty Duke. And since it's the first instance, we're going to have to find which week it appeared first on the chart. It's actually probably none of these because the first one says week 4. It's probably somewhere else in the data frame. These aren't necessarily in order. And we're going to figure out the URL, and then after all this stuff, we're going to append it to unique song IDs and append the URL as well. When we get to the second row, we're going to see the same song ID, so we have to just ignore that one. So we have to check the other song IDs that have already been added and make sure it's not in there. So the vector I'm going to use to track this, or the object I'm going to use to track this, is called inVector. And then we're going to loop over the unique song IDs and check whether the kth one is equal to this one. And if it is, we're going to set inVector to true. And then down here, we're going to check this inVector thing. So if it's true, not inVector will be false, and we'll just ignore this. So that means if we've already calculated the first URL for this song, we're going to get a true here, and we're going to just ignore this part. But if we haven't already calculated the first URL for this song, we're going to get a false. So none of these will show up as true. And then we have to execute this code. And the way this code works is we look at all of the song IDs and figure out which indices correspond to this song ID, the one we're looking at right now. We'll store that in ins. We create a smaller data frame called subhot, which just pulls out those indices. So subhot, so in the first iteration, subhot will contain, actually I could just run this on Patty Duke. Actually, we won't do that because we've changed hot1e4. I can run it in debug mode for you in just a second. So this will contain just those entries for Don't Just Stand There by Patty Duke. We find the minimum week, so we look at the week ID for subhot and figure out which one is equal to the minimum. So that's the row of the minimum week. And then we update things. We update it with this song ID, and then we pull out the URL from that particular row, and then we move on to the next one. Okay, so let's go back here. Actually, let's go back here. I'll just run this in debugging mode just so you can see. Okay, so we're in the browser. Okay, let's jump through this. So right now, unique song IDs is empty. First URL is empty. And then we're going to run through this loop. So right now, this song ID, that's the first one in the sub data set. And there are no other song IDs, so that loop actually gets skipped, which means in vector is false, which means it's going to enter this if statement. There's actually only one entry for this song. So sub hot should be a data frame of 1 row, and which means the min week is that one. And now unique song IDs is that one, and first URL is this one. Okay, so that's how that works. And let's exit that, and let's get back here. Okay, so the first thing I'm going to do is just run that function and time it. Oh, I need to get rid of this. It's running now. Okay, that took 11.9 seconds. So it's slow. So we did a very small subset of this data set, and this method took 11.9 seconds on that very small subset. So this is going to be unacceptable for the task. It's too slow. The problem is we don't know why it's slow. And to figure out why it's slow, we need to run it through a profiler. So what a profiler does is it runs the code and it makes some measurements of how long each part of the code takes, and then generates a report for you. I said before that there were no good tools when I started learning R for doing profiling. That's not quite true. There always has been a tool called rprof. So you could have always profiled your code with rprof, but it's kind of hard to use. It doesn't generate like a nice visual output. Kind of just prints out a table, so it wasn't nearly as good as the MATLAB profiler. There's something newer now called profvis, which is very good. I think it comes pretty close to the MATLAB profiler. All right, so it's in library profvis, and the way it works is you call the profvis function, and then inside of curly braces you put the code that you want to profile. And it's best to put your code that you want to profile in a separate file, and then source the file, and then run the function that you just sourced. So method 1 is one of the functions in performancefunds.r. So I'm going to source it and then run the result. So let's just do this. This is again going to take, I think, about 12 seconds, but it's going to pull up a nice little report for us. Okay, here we go. This is the report. You can see at the top it has my code. So here's the thing that got run. This is telling us, if I move over here, this used this time 11.18 seconds. So these are in milliseconds. And this is how much memory got used. So it used a lot of memory, 1,200 megabytes. And then down here, it has a separate panel for performance funds. And this is kind of cool. So it runs through each line of the code, and it's telling you over here how much memory each one uses and how much time it used. So basically, if you look at this, if you profile your code and it looks like this, you should be excited because you see that there's one particular piece of the code that's taking a long time. So if you can figure out how to make that particular piece run faster, you're going to make your whole code run a lot faster. Okay, so it's taking a long time to compare the this song ID to each of the existing unique song IDs. So that part is pretty slow. Otherwise, things run faster in comparison. Now down at the bottom, it has this thing. Basically, this is, you read this left to right in terms of time. And each little piece tells you what is happening during that time. So at all times, it's calling the method1 function. But within the method1 function, most of the time it's doing this if unique songs k equals this song. And then within that, there's other operations. Sometimes these are kind of, GC means garbage collection. This is a memory operation. Sometimes it's kind of hard to figure out as you go higher and higher into the call stack. It's hard to see what that stuff means. But this gives another visual representation of what the code is doing at certain times during the operation. All right, so that's great. We know what the slow part is by profiling it. So let's go in and let's try to write a new method that runs faster. So there's going to be something called method2 that we're going to look at next. Let's see. So that was the slow, this was the slow piece of the code. And so what method2 does is it does something a bit smarter here. So we figure out which song ID we're looking at. That's the same as before. But instead of looping over all the song IDs and checking whether this particular song ID is one of them, we're going to use the in operator. This should be a little bit faster. And there actually are faster ways than this to do it. So that's the in operator. So basically this says it's going to return true or false if this song ID is equal to any of these. If it's equal to at least one of them, it's going to be true. If it's equal to none of them, it's going to return false. This does exactly what we need it to do. Otherwise, the code is exactly the same. All right, so let's run that one. We're going to run it on the same sub-data set. Oh, and already we can see that that ran much faster. So now this took about 1.3 seconds. It used less memory. And if we go down, we can see what it was doing. Now it spends not the majority of its time checking whether this song was already looked at. It's spending its time on other things. So it's checking whether, or it's finding the right indices for this song. It's subsetting the data set and doing this append operation down here. All right, so we made it a lot faster, but that was only a very small subset. Oh, before we move on, an important thing when you're tinkering with your code trying to make it faster, you have to check that you don't introduce a bug that gives the wrong answer. So there's a few functions that allow you to check whether your answer is the same. So if we trust result 1, we'll want to test result 2 against it. And identical and all.equal are two different functions for, and they do slightly different things if you want to read the documentation, for checking whether the two results are the same. So in this case, they are, so we got it true. That's good. Okay, now we were working on a much smaller sub-data set, and when you work on smaller versions, you may not get results that are particularly meaningful for the big problem you want to solve. So there could be scaling issues that some parts of the code run perfectly fine on small data sets, but when the data sets get really big, something else, or that can become the bottleneck. So let's look at a larger version. This will have 100,000 rows. And we're going to run the same method again, method 2. Still running. Still running. Oh, just finished. Okay, so that took 22 seconds. And let's look at the report. Okay, now you can see that on the bigger problem, something else is sticking out. It's this thing, which didn't stick out before. Let's see. This was the slowest one, but it was about the same as doing the subsetting. Now this part is much slower than doing the subsetting. So we should, if we want to make it faster, we should focus our energy on making this part faster. Okay, so what does this do? It looks at the song ID, which is a character string, and this song ID is a character string, and compares it to every entry of hot $song ID and checks whether it's true or false. So this is now the slowest part. Now you may decide that, okay, this took 22 seconds on the smaller data set, which is about a third or quarter the size of the full data set. And so if it takes a minute or two to run, maybe that's fine if you only have to do it once. And so at this point you might just quit and say, okay, it's fast enough, I don't need it to go faster. But for some cases you may need it to run faster. So we're going to look at different solutions to that. So I've kind of written this up the way I tried to optimize it as I was writing this code. So you'll see the next one doesn't help, but we're going to still go through it. So let's look at method 3. So in method 3, I thought, I've heard that which can be slow, and it's unnecessary in this case. So if you do if you don't include the which here, you just keep it as a true-false vector, this will still work as intended. So that's the only change in method 3 here. And this actually makes things slower. While that's running, let's look at method 4. So in method 4, maybe it's because we're doing a string comparison here. And maybe if we use a factor, which has kind of it's integer representation underlying the string representation, maybe that will run faster. So what I'm doing here is I'm first converting song ID to a factor, and then otherwise all the code is exactly the same. Okay, so method 3 just finished. You can see now it's 35 seconds instead of 22. So that actually made things worse to not use the which. So here's this one. Yeah, this was still much slower. Actually, the slow part now is this. Okay. So by using true false here, let's see, did I make that faster? Yeah, it made this part a little bit faster, but then it made the subsetting much slower, which I didn't expect. So this is why you have to time the code. You don't know what the result is going to be until you actually time it. All right, so that was a bust. So we're not going to be using method 3. What method 4 does, I just showed you, is the factor version. And I'm going to run this on the smaller data set because there's going to be an issue with this as well. Well, one of the issues is that it's slow, but it also gives the wrong answer. Should finish up here. Okay, so this clearly is not going to fix our problems. Oh, now it's done. This also took 35 seconds. And it also gives the wrong answer. Let's just look. I want to show you why it gives the wrong answer. So remember, method 4 is the factor version. And so result 1, it has unique song IDs, which is a string vector. And here they're integers. So this has to do with the factor representation. And let me show you in the code where things go wrong. Actually, we can insert a browser, because I think this could be instructive. Oh, I need to source it first. Okay. All right, so that converts to factor, empty vectors, and now let's step into the loop. Okay, so this song ID is that. My Shoes Keep Walking Back to You by Guy Mitchell. It's not going to be in the vector because the vector's empty. And if we look at ins, there's 2 entries for this song. Row min week is the first entry. And right now, unique song IDs is an empty vector. But when I run this, even though this song ID is a factor, when I append it to this empty vector, now unique song IDs represented it as its integer form, 4583. So that's not what we want. So not only is this method slower, it gives an answer that we don't like. So let's kill this and get out of there. And method 5 fixes that. And in method 5, we create something called song ID factor. So it's a separate variable. We pull out this song ID and this song ID factor. We do the comparison using song ID factor, but then we update this vector using song ID. So let's run this. And that one took, again, about 30 seconds, but I paused the video to save you the torture. So let's look at the profiler. Actually, it only took 20 seconds, so it was a bit faster. If we scroll down to method 5, you can see it's still spending a lot of time in this operation. So converting it to a factor really didn't help us much. I thought that would help, but it didn't. This is why you have to kind of experiment and time the code. What I really want to do is, I don't care that song ID is a factor. I just want to do a numeric comparison instead of a string comparison, because I think that's going to be faster. So in, oh, by the way, this gives the right answer. In method 6, we're going to use a numeric representation. So we're going to take song ID, we're going to convert it to a factor, but then we're going to strip away all the factor information by just converting that to a number. So we're just going to keep the underlying numbers associated with the factor levels. And we're going to call that song ID numeric. And we're going to do the comparison using song ID numeric. But then we're going to save the song ID. All right, so let's run that one. And that was much faster. That took 1.1 seconds. But we got to try it on the bigger data set. Now it's taking much less time in this step. But this step is still, so now this step is the slow step. We get the right answer, that's good. And let me just run it on the bigger one so we can see how it scales. Still running. Okay. I think before we got 20 seconds or something. Where was it? Yeah, 22 seconds for method 2. And now we are at 13.9 seconds. So it is faster, but not blazingly fast just yet. Still, this is the bottleneck. And now we're creeping back towards this being a slow part. So that could probably be sped up. So let's look at, oh, by the way, we get the right answer. That's good. Let's look at a new method, number 7. So method 7 is kind of vastly different. So before we were building up these unique songs in the first URL one by one. And so each time we have to check whether it's in the list. What would be a better idea is just take the data set and split it up by song ID and then operate on each split in turn. That way we don't have to check whether we've already done the calculations for that song ID. So in method 7, we're using the split function. The way the split function works is you take a vector or a data frame called, so this we're going to use the hot data frame, and we're going to split it by song ID, which means we're going to return a list. So split hot is going to be a list. Actually, let me just run this. Should work. So class split hot is a list, and split hot 1. This is the data frame containing the data for the first song ID in whatever order they picked, which was Twistin' White Silver Sands by Bill Black's Combo. And this song just squeaked into the top 100 for 2 weeks back in 1962. So this is easier because first of all, we can say what's the length of split hot, 29,389 unique song IDs. That allows us to initialize these because we know how long they're going to be. And we can just loop over split hot. So this here, we'll loop over split hot. We'll pull out the song ID. We'll find the minimum week. So this is a slightly complicated piece of code, but it does the same thing as this piece of code. And then we assign the first URL. Okay, so that's method 7. It uses the split function. And we're just going to go for it because this one's faster. We're going to run it on the entire data frame. Okay, so that's great. So this took 2.2 seconds on the entire data frame. And you may decide, okay, I'm done now. I've done enough optimizing. 2.2 seconds is plenty fast for my objectives, and just be done with it. But we're going to go further. So I want to look at the profile. Okay, now you can see that the profile is not really giving us useful information anymore. Basically, it's saying that, well, first of all, if you add these up, this is 0.05, 0.1, and 0.4. So this is about 0.2 of a second if you add these up, whereas the whole thing took 2.2 seconds. So something's odd is going on with the profiler in that it's not really timing each piece of code. So that's a bit weird. So maybe we can't really trust the profiler in this case. Sometimes that happens. The profile's not perfect. It's a useful tool, but it's not the only tool and isn't always give you the answer you want. So let's explore some other ways of timing our code. So in method 8, let's see. I really want to figure out how much time each takes. In method 8, Okay. So method 8, we're going to use the split function again. But what we're going to do is I want to try to avoid this complicated operation here. I want to set up the data set so that I can always it's always going to be in the right order. So then I can just pull out the first entry, and that will be the minimum week. So to do that, I'm going to pre-sort the data frame. So right here, I'm converting week ID to a date. I'm not sure this is necessary, but I'm doing it anyway. I'm computing the ordering of these dates. So that's ord. And then I'm creating a new data frame called hot ord, which orders hot according to the date. So hot ord will automatically be in chronological order. Then I do the split on hot ord according to song ID. And then instead of doing that complicated operation, I just grab the first week. Let's see, that code's not right. This should say URL, not week ID. I'm just pulling out the first URL because it's already going to be in order. And then return the list. On top of that, I kind of skipped over this. I'm going to print out where we are in the code, and so that we can kind of watch the code run and see what's taking the most time. Okay, so we're not going to profile this. We're just going to run it and time it. 3.2 seconds. Let me do this again. So it spends a little time calculating the date, but actually most of its time is the split. So it's pretty clear that the splitting is the bottleneck now. Remember, that didn't show up in the profiler, but we can clearly see that the splitting is the slowest part now. Okay, so one thing is that there's a lot of information. If we do head hot, there's a lot of information in this data frame that we're not actually using. We don't use the week position, we don't use the song or the performer or any of these last 4 columns. We actually only use the week ID, the song ID, and the URL. So one thing about writing performant code is one of the slow things that happens is moving things around in memory. So if you can work with smaller objects that take up less memory, things tend to run faster. So here I'm just sending in a data frame that contains the columns that I need, week ID, song ID, and URL. Before it was taking about 3.2 seconds. And now it's down to 2 seconds. So just by being minimalist about the data that I send it, I can get a big speed up. Okay, so that was the exact same method, just sending it less data, no unnecessary data. So let's look at method 9. Method 9 is going to double down on that principle. When we do the splitting, so we only use week ID to do the ordering. After this piece of code, we never use week ID again. So to do the splitting, I'm only going to split a data frame containing the song ID and the URL, because those are the only things I use down here. Okay, so this should run a little bit faster. Now 1.6 seconds. Good idea to run it a couple of times. 1.4 seconds. 1.4 again. All right, so that's a bit faster. So the principle here is don't push around data inside your computer that you don't have to. Use the minimal amount of data that you need. All right, for most purposes, 1.4 seconds is going to be plenty fast. But if you're crazy like me, you're going to want to make it go faster. So let's look at method 10. In method 10, we're going to use tapply. So we've looked at tapply before. Basically, the way tapply works is that you apply this function. So here I'm just pulling out the first entry to this object, but separately for each group according to this object. So what this does is it's going to pull out the first entry of this object, the URLs, separately for each song ID. And if you look at the documentation for tapply, well, let me double check this. I think it talks about using the split function. Okay, it doesn't necessarily use the split function, but the first argument is an R object for which a split method exists. So the first argument has to be splittable. So it could be a vector, it could be a data frame. And then the second argument is what you're splitting on. This is could be multiple things, a list, but these are things like factors. Okay. Or something that could be converted to a factor. So song ID could easily be converted to a factor. Okay. And we're going to use the same method. We're going to reorder it. And then we're going to run tapply. So the return value is going to be different. We'll look at that in a second. But here we're using the principle that we should use the more specific function for the task that we need. So if we first, up here, we're first splitting it, and we're generating this object split hot, which basically it has too much information. It's an object that's actually not needed to store anywhere. It's only an object that we're pulling things out of and saving. So tapply is going to kind of avoid that storing that split object and get directly to the thing that we need, which are the first URLs. Okay, so let's see method 10. Okay, now this runs in less than a second, so we've gotten more specific and it's going faster. You can see the return value is different. We're not going to worry about that, but it's now a named vector. So you could extract the names and put it into a list if you wanted to, but I actually like the name vector. It's a simpler object. Okay, let's run that again. Yeah, this takes about 7/10 of a second. So that's still faster. Again, you may decide that that's fast enough, but let's keep going. Method 11. What's 11 does? Okay. Maybe we don't have to convert to a date first, because you can order strings, and I was curious to see if just ordering the strings ran faster. So that's what method 11 is. And no, it's slower. So it's worth it to first convert it to a date and then order the dates rather than to try to order the strings. Okay, that's good to know. Then I became curious, okay, so suppose you have to do a lot of operations on this data set, and let's just do this ordering once and then see how fast it goes when you assume that the data set has already been ordered. So maybe it was probably a good idea when you created the data set to just save it in order, and then you wouldn't have to worry about all this ordering stuff. So I want to see how fast it goes if you can assume it's already ordered. So that's result 12. Let's just look at the code. So what result 12 does, basically, it just does the tapply, because you're assuming that it's ordered. So hot ord, do this. Okay, and that's even faster. That's about 1/4 of a second. And then we can go faster. So tapply, just like the apply example we looked at before, it's probably too general of a tool for what we want to do. Because it's just doing this really simple function, but it's pulling out the first entry of the URL for each song ID, which is just a really simple operation. There's got to be a more direct way to do that. So the function I'm going to use is called duplicated. This is a really useful function in R. And let's look at this. Dupes. And we'll do okay. So duplicated will return true if the vector, the input vector, has already appeared. So the first entry is always going to be false because nothing has appeared yet. But here the second entry is true because this one has already appeared. And then 2 through 8 are all false. And then 9 is, sorry, let me say that again. 2 through 8 are true because they are duplicated. 9 is false because this is a new one. And then you get true, 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 true. And then for this one, you get a false. This is going to be really useful because we're just going to subset the data frame to take the not duplicated ones. And just pull out the song ID. So again, we're going to assume it's ordered and just grab the first one, which is exactly what duplicated does. So let's look at method 13. Okay, and that's really fast. That's 0.03 seconds. And we followed this principle of just doing the most specific task and using the most specific function for what we want to do. Even tapply, which was much faster than all the other things we tried to do, was too general a solution. So using duplicated runs much faster. Are these the same? No. There's probably something about it that's different. I do think this gives the right answer, though. Maybe it's in a different order or something. Okay. I did want to go back and say, how much longer will it take if we don't assume it's order, just for fun? So this does the ordering. It doesn't convert it to a date. I don't know why that's slow or why it works here, but I think this worked okay. So this 14 is the same as 13, but we're not assuming ordered, basically. Oh, that is slow. Okay, let me fix this real quick. I want to use the order by date. Yeah, this should do it. As.date, order. Okay. Okay, so the ordering takes a significant amount of time. Now we're back up to about 0.6 seconds. So probably the right thing to do would be to just order it once and then write functions that assume it's ordered. That runs really fast. Okay, so that's it for performance at this point. There's a lot more to learn about this, but I think the way that you learn is obviously by reading, watching videos and all that, but just when you write your own code, run it through the profiler, and then you'll start to get a sense over time of how to write the most efficient code. All right, thanks. See you next time.